Look at a passenger airplane, hundreds of people inside, tons of cargo underneath, and somewhere inside that giant machine, tens of thousands of liters of fuel. But here's the strange part. That fuel isn't mainly stored where you'd expect it. It's inside the wings, and honestly, that sounds like a terrible place to put it. The wings are thin, they're constantly flexing, they're exposed to the outside air, and they're carrying the entire airplane through the sky. So why would engineers turn the wings into giant fuel tanks? The answer isn't simply because there's space. There's a much more interesting reason. And once you understand it, you'll realize the fuel isn't just powering the airplane, it's actually helping the airplane fly. The first explanation seems simple. Airplanes need somewhere to put fuel, and the fuselage is already packed with passengers, luggage, cargo, and equipment. So why not put the fuel in the wings? Makes sense, but that can't be the whole story, because engineers could put fuel almost anywhere. They could build larger tanks underneath the fuselage. They could put more tanks toward the rear. They could even distribute the fuel throughout the aircraft, but they don't. And that's because airplane fuel isn't just a storage problem, it's a weight distribution problem. Imagine carrying a heavy backpack. If the weight is positioned close to your body, it's manageable. Move that weight far away from your body and suddenly it becomes much harder to control. An airplane has the same problem, except instead of a backpack, it's managing tons of moving mass while traveling hundreds of kilometers per hour. That brings us to one of the most important invisible points on an airplane, the center of gravity. Every airplane has a carefully calculated center of gravity. Think of it as the point where the aircraft's total weight effectively acts. And engineers have to keep that point inside a very specific range. Too far forward, and the aircraft requires more control force to maintain its pitch. Too far backward, and the aircraft can become less stable and more sensitive to disturbances. Now here's the problem. Passengers don't stay perfectly still. Cargo changes from flight to flight, and fuel is constantly disappearing. Every minute the engines are running, the airplane is becoming lighter. So if you put a huge amount of fuel in the wrong location, burning that fuel could significantly change the aircraft's balance. But the wings offer a clever solution. They're positioned close to the aircraft's lifting structure, and near the region where engineers want the aircraft's mass distributed. So as fuel is consumed, the aircraft's balance changes much less dramatically. That's important, because the airplane doesn't want to spend the entire flight fighting its own changing weight distribution. It wants to remain predictable. But there's another reason. Look at an airplane wing from the outside. It looks surprisingly thin. You might imagine there's barely enough room inside for anything. But the wing is actually a complex structural framework. Inside are spars, ribs, panels, control systems, and other structural components. And between all of those structures, there is usable internal volume. Aircraft designers can seal that volume and turn portions of the wing itself into fuel tanks. This is commonly known as a wet wing. Instead of putting a separate container inside the wing becomes the container. And that is incredibly efficient, because the structure already has to exist. The aircraft needs the wing whether it carries fuel or not. So engineers are effectively using space that's already built into the aircraft. Meanwhile, the fuselage is extremely valuable. Every cubic meter inside the fuselage could be carrying passengers, luggage, or cargo. If you put fuel there, you're potentially sacrificing payload. The wing doesn't have that same economic problem. So now we have two advantages: better mass distribution and efficient use of existing structure. But we're still missing the most clever part. Here's where airplane design gets really interesting. During flight, the wings generate enormous lift. That lift acts upward along the wings. Meanwhile, the weight of the aircraft acts downward, with much of the airplane's mass concentrated around the fuselage. This creates enormous bending forces. Think of the wing like a giant beam attached to the aircraft. It's constantly trying to flex. And the area where the wing connects to the fuselage, the wing root, is one of the most heavily loaded parts of the entire structure. Now imagine the wing is empty. The wing still has to generate lift, but its own mass distribution isn't helping much with that load. Now fill the wing with fuel. That fuel is distributed throughout the wing, and that mass changes the way the wing responds to the forces acting on it. In simple terms, the fuel helps counter some of the wing's bending loads. The wing doesn't have to carry all of the structural burden in exactly the same way. This can reduce bending stresses and help manage fatigue over the aircraft's lifetime. So the fuel is doing something surprisingly useful. It's not merely sitting there waiting to be burned. Its location is part of the aircraft's structural design. That's the part most people miss. When the airplane is on the ground, fuel is pumped into the aircraft through dedicated fueling connections. The fuel then enters the aircraft's fuel system and is distributed into the appropriate tanks. And the fuel itself isn't ordinary gasoline. Large jet aircraft use aviation turbine fuel, essentially a highly controlled aviation kerosene-type fuel designed for the extreme conditions of flight. At cruising altitude, temperatures outside the aircraft can become extremely cold. The fuel therefore has to remain usable at temperatures that would be completely unacceptable for ordinary automotive fuel. And the fuel system itself is built with redundancy. Multiple pumps, valves, feed paths, and backup systems help ensure that an engine can continue receiving fuel even if one component fails. So when you look at an airplane and see fuel inside its wings, you're not looking at a simple tank. You're looking at part of a fault-tolerant system engineered around weight, balance, structure, temperature, and reliability. And that's what makes the wing fuel design so clever. At first, it looks like engineers simply needed somewhere to hide a huge amount of fuel. But look closer. The wings provide existing internal volume. They keep valuable fuselage space available for passengers and cargo. They place fuel in a useful location relative to the aircraft's center of gravity, and the distributed fuel mass can also help manage structural loads. Meanwhile, the fuel system carefully controls how that mass moves through the aircraft as the fuel is consumed. So the airplane isn't just carrying fuel, it's managing fuel as part of the entire machine. And this is a recurring pattern in aviation. The best engineering solutions rarely do just one job. A component that looks like a simple storage tank can simultaneously become part of the aircraft's weight management strategy, its structural system, and its overall efficiency. So the next time you look out an airplane window and see that enormous wing flexing beneath you, remember what's inside it. Not an empty shell, not just metal and cables, but a carefully engineered system carrying a massive amount of energy, while simultaneously helping the airplane manage its own weight and structure. The fuel isn't simply stored in the wings because the wings have room. The wings were designed so that the fuel could become part of the airplane's engineering solution. And that's the fascinating thing about aircraft. Sometimes the most important technology isn't the engine, it's the part you barely notice. Quietly doing several jobs at once, that's engineering, and that's why airplanes keep their fuel in the wings.